Welcome to our dynamics video. This is Ben Presley along with Ryan Meisberger. Right now I'm drawing out an FBD for a door closer. You see these every single day. They keep doors swinging at a safe rate. And we're going to do a little problem to see how it actually works and how it all relates. Alright y'all, it's time to solve this equation. Alright, so first we are going to use our knowns, which we actually know a lot about this problem. We know the inertia of the door, which is simply equal to 1/2 ml squared. For our m, we are going to use 40 pounds divided by 32.2 because that is the average weight of the American door. The average length is 36 inches, but we need to convert that into feet, of course. And we just need the inertia about, right now we're just going to focus on the centroid, but more on inertia later because it's very important to this problem. Alright, so here we get I bar equal to 1.86. That's alright. So our goal is to get the door to swing under 1.5 feet per second. So we're going to use an energy problem here because we know a lot about the right hand side. Let me explain. First I'm going to draw my free body diagram now. And I want to label our instant center of rotation. This will be extremely crucial later. And then we have VE, which, like I just said, we hope it's less than, oh, that's a typo. It's supposed to be feet per second. And then our VB is where all the forces are happening. So we need a way to relate VE to VB. And we are going to do this through something called similar triangles. And it's actually a really easy relation in this case. It is simply, well, let me just write it down. So we see that VB is just going to equal 1/3 of whatever VE is. Well, we know VE, that's 1.5 feet per second. So we can actually solve for the right-hand side of the equation. But remember, what I just solved right here, 1/2 mv squared, is only the translational energy. We need to focus on the rotational energy as well, because the door is rotating when it opens. And coming back to inertia now, right now we know the centroid inertia. We need to move this inertia to point B, which is simply at the top of the door about 1/3 from the hinges. So with these calculations, we are moving the point of inertia to where all the forces are happening, which is at point B. Alright, now we're going to solve. First, we need to see how the forces of the spring affect the gear and pinion system. I really want to emphasize this next step. Here we are assuming that the pinion is 1 inch thick with gears that stretch out 2 inches from its center. This lets us set up a moment equation for the force spring and the force of the door / arms on the pinion. So what we see here is that force spring is equal, to the constant times the distance it travels. And the distance it travels is limited to how big the box is. So this is why I'm calling this part the mechanical design, because we care about the length of the spring, the length of the box, as well is the force that's going to be exerted by, the human on the door. So now I'm going to solve our equation. Now we know the left-hand side and how it all relates to each other based on my moments equation. And I'm going to equal that to what we solved for on our right-hand side, which is the max amount of energy we can allow safely based on the end of the door swinging no more than 1.5 feet per second. So that ended up being 24.41 joules. So now I'm going to plug in what we solved for in the moment equation. So the last thing we need to solve for here is D in the work equations. So what we're going to do is, we know the circumference of a circle, right? So we're just going to multiply that by 1/4 because that's about how much a door swings open, right? So here, just plugging in the radius of the door, or the length of the door, sorry, we get 1.57 feet as our total distance. Next, we're going to plug it all in and equate, we're going to solve for force of the human on the left. And I'm going to explain our final equation in a second. The reason we have force human on the left instead of the right is because, you know, the force of the human varies on the work environment. Like, if you're working with a bunch of lumberjacks, they're going to be strong. They're going to be throwing the door open hard. Thus, you're going to need to make your right-hand side bigger by increasing the constant of the spring and the size of your door closer. And this makes sense, right? If you have a large force on your left-hand side, you're going to need a big constant, a big door closer on the right to just make sure that door isn't flying open at more than 1.5 feet per second. And that is why I said earlier, this is a mechanical design problem. We can't really say exactly, you know, what the constant is, because it'll vary. We want it to vary. You know, one door closer doesn't fit all, and that's our project. We were really stoked about this, and we actually did some examples. Our K checks out, but we just don't have time to show it in this video. So thank you for watching, and I'll see you later.